Hello viewers, today I am going to talk about engineering materials, and the first section of engineering materials is structure of crystalline solids. The brief outline of the talk is as follows: crystalline and non-crystalline solids, crystal lattice, unit cell, Miller indices and Miller planes, principle of X-ray diffractions. Now let us know in detail about these outlines. Crystalline and non-crystalline solids. What is the difference between crystalline and non-crystalline solid? Crystalline solids are those solids in which the atoms are arranged in periodic fashion. Now crystalline solids are categorized into two types. First one is single crystals, in which atoms are arranged in the same orientation all along the solid, and the second one is polycrystalline solid, in which there are many orientation of atoms throughout the solid. Now non-crystalline solids are those in which the atoms have no particular orientation. Sometimes they are also called as amorphous materials. Now when we talk about crystal structure, we need to know some very basic definitions, and with those definitions we can understand crystal structure in a better way. So the first one is lattice. Now the definition of lattice is: it is an infinite set of points defined by integer sum of linearly independent primitive lattice vectors. Now as you can see in this image, there are periodically arranged lattice point. Now if I want to represent a particular point vectorially, then I can represent that particular point by a vector r, which is equal to n1 a1 plus n2 a2, where n1 and n2 are integers and a1 and a2 are primitive lattice vectors. There is an alternate definition of lattice, which says it is a set of points where the environment around any point is same. Now the next definition is of unit cell. It is a repeated motif which is the building block of a periodic structure, and unit cell is not unique. As you can see on the right hand top side image, there is a structure of crystal lattice which is represented in three different ways. So each small block represents a unit cell. So in that sense we can say that the unit cells are not unique to a crystal lattice. Now the next definition is of primitive unit cell. It is a unit cell having exactly one lattice point. And now the next definition is for conventional unit cell, which is a unit cell which is not primitive but easy to work. So most of the time we will use primitive or rather conventional unit cell to define the lattice structure. Another important definition is of basis. You will most often use basis to define crystal structure, and the definition is: it is the lattice points with respect to a particular reference point in the crystal lattice. As you can see in the figure, there is a set of lattice point, and in which we are considering only a particular area which is a dotted square, and this square has a length of a. Now if you can see, there is a black dot at the leftmost corner of this dotted square, which is our reference point, and inside this dotted square there are 5 lattice points, 4 of which are grey color, which is smaller in size, and the central one is light gray color, which is bigger in size. Now, if we want to represent these points in terms of basis by using the side length of dotted square, then we can start from the leftmost corner and we can go in counterclockwise, and it goes like this. The leftmost point is denoted as a by 4, a by 4, then the next one is denoted as 3a by 4, a by 4, then the next one is 3a by 4, 3a by 4, and the last one is a by 4 and 3a by 4. Now, if we represent the central lattice point, that can be represented by a by 2 and a by 2. Now, so far we were talking about 2-dimensional lattice structure. Now, if we extend it to 3 dimension, then the simplest of structure coming to our mind is simple cubic structure, which is a cubical structure having 8 lattice points at the 8 corners, and all the side lengths of the cube are of same length. And if we take a lattice of simple cubic structure, then a particular point in the lattice structure can be represented by u v w, which represents the coordinate of that point, and vectorially it can be represented as u a 1 plus u a 2 plus u a 3, where a 1, a 2, a 3 are the primitive lattice vector in 3 coordinates. Now, if we imagine this simple cubic by filling the corners with hard sphere of radius r, then we can have a relationship between the radius of this sphere with the side lengths of the cube in the following way, which is A is equal to 2r. Now, if we want to find out the total number of atoms in the unit cell, then we can use the following formula, which is n is equal to ni plus nf by 2 plus nc by 2, where ni represents the total number of atoms within the cube and nf represents the total number of atoms on the side faces of the cube, whereas nc represents the total number of atoms at the corners of the cube. Now, if you use this particular formula, then for simple cubic we get only one atom per unit cell. There is another important point to be noted is coordination number. It is the number of nearest neighbors to a given point in the unit cell, and for simple cubic this is equal to 8. Another important thing to be considered is the atomic packing fraction, which is defined as the volume of all atoms in unit cell divided by the volume of unit cell, and for simple cubic it is equal to 0.52. The simple cubic structure can have different structure where the side length of one particular coordinate axis is different than the other two, which is called a tetragonal unit cell, and the other one is where all the 3 side lengths are of different magnitude, and this structure is called orthorhombic unit cell. Now, the next 3-dimensional lattice structure which can be represented by a unit cell is called body centered cubic. It is same as the simple cubic structure, except there is an atom inside the unit cell which is lying at the center of the simple cubic. Now, if we draw a relationship between the side length A and the radius of the imaginary solids that we place in the unit cell, then we can get a relationship like this, which is A is equal to 4r by root 3, and for this the total number of atoms in the unit cell is equal to 2 by using the previous formula. The coordination number for this unit cell is equal to 8, and the atomic packing fraction is equal to 0.68. The next 3-dimensional unit cell is face centered cubic, which has 8 atoms at 8 corners, and there are 6 more atoms on 6 faces of the cubic structure. The relationship for this unit cell for A and R is A is equal to 2 root 2 R. The total number of atoms in the unit cell is equal to 4 by following the formula discussed in the previous section, and the coordination number and atomic packing fraction for the unit cell is 12 and 0.074 respectively. And the final unit cell structure is hexagonal closed pack structure. It is a structure where 2 hexagonal planes sandwich a layer of atoms, and the separation between the 2 hexagonal plane is represented by C, and the relationship between C and the lattice constant A is equal to C by A is equal to root over of 8 by 3. Number of atoms in the unit cell is equal to 6, and the coordination number for this particular unit cell is 12, whereas the atomic packing fraction is 0.74. Now, every crystallographic plane in the crystal is defined by Miller indices, which is represented by 3 notations, that is H, K and L. To find out H, K, L value for a plane in the cubic unit cell of side A, B, C, following steps are to be taken. The first one is, if plane passes through origin, choose a different origin. Once that is done, we will have to find out the intercept to the x, y, z coordinates for the plane, and which can be denoted as A, B, C. Then we have to consider the reciprocal of the intercept, that is 1 by A, 1 by B and 1 by C. Once we get the reciprocal, we have to normalize by multiplying with A, B and C, that is A by A, B by B, C by C, and if needed, make smallest integer of these normalized value by multiplication or division of common factor, which gives us the Miller indices, which is H is equal to Na by A, K is equal to Nb by B, L is equal to Nc by C. Now, some of the examples of crystallographic planes are within bracket 100, within bracket 110, within bracket 211. If the intercepting point is residing in the negative direction, then the plane can be represented in the following way. Whichever coordinate is in the negative direction, that particular Miller indices will be represented by a number with a bar on top of it. For example, 1 bar 0 1 within bracket, 1 2 bar 0 within bracket. In cubic crystal, 1 1 1 within curly bracket represents a family of planes of 1 1 1 within bracket, 1 bar 1 1 within bracket, 1 1 1 bar within bracket, and so on. Now, if we want to take an example to understand Miller indices, we can use the following example given in the image. Now, we want to find out the Miller indices for the plane represented in yellow color. Now, as we can see, the plane passes through the origin, so we have to shift the origin. Once we shifted the origin, we can see that the coordinates or the intercepting points for this particular plane in xyz direction is as follows, that is A is equal to infinite A, B is equal to minus 1 B, C is equal to C by 2. If we take the reciprocal, it is 1 by infinite A minus 1 by B, 2 by C, and if we normalize this by multiplying A, B, C, then we will get the normalized value as follows, which is 1 by infinity, minus 1 and 2. Because we are getting integer values, we do not need to multiply or divide with any smaller factor. So, the Miller indices for this particular plane is represented as HKL is equal to 0, 1 bar 2. X-ray diffraction and principle. So, the principle of X-ray diffraction is when waves scattered from regularly spaced obstacles and the obstacles which can scatter the waves and which are equally spaced, and the spacing between the obstacle is of the order of the wavelength of the waves, and after scattering from these obstacles we will come across interference, and these interference pattern will be constructive or destructive depending on the condition. And for constructive interference, the condition is that the path length between the two waves should be equal to the integer multiple of wavelength. For destructive interference, the path length should be integral multiple of half wavelength. Now, why do we need X-rays for understanding the structure of solids? Because the wavelength of X-rays are of the order of the interatomic spacing in the solid. And if we consider two X-ray waves which incident on a solid on two different atomic planes at an angle theta, and these two waves are coherent monochromatic in nature, and if the interatomic spacing or the interplanar spacing between the two planes is denoted by DHKL, then we will say there will be a constructive interference when the path length between the two waves is equal to n lambda, where n is integers. Now, as you can see from this image, the path length is SQ plus QT, which should be equal to n lambda to give you a constructive interference, and this path length is 2D HKL sin theta is equal to n lambda. This particular formula is called Bragg's law, and we have a relationship between the interplanar spacing and the Miller indices by using the following formula, that is DHKL is equal to 1 by root over of h square by a square plus k square by b square plus l square by c square. Now, in Bragg's law, n defines the order of diffraction. So, Bragg's law needs to be satisfied for constructive interference and hence diffraction. Now, though Bragg's law is essential to understand the crystal structure of solid, it is not sufficient condition to get the structure of the solid. Now, this gives us information about crystals having atoms at the corner of the unit cell, but what about when you have atoms at the center of the unit cell or at the faces of the unit cell? In that case, we will have two more conditions. For example, if we have a face centered cubic, then in that case the Miller indices, that is H, K and L, are either all odd or all even numbers. Similarly, for BCC lattice, we should have H plus K plus L should be equal to even number. So, if these two conditions satisfy along with Bragg's law, then for FCC and BCC we can determine the structure as well. So, powder diffraction method is the most common method to study the structure of solid. So, the instrument which is used for studying the crystal structure is called diffractometer. There are many other ways to find out the structure of solid, such as electron and neutron diffraction method, but the materials of interest are of different in nature. Neutron diffraction is different than X-ray diffraction in a way that for neutron diffraction the solids or the materials that we use are having atoms which are having low mass, but if we think of X-ray diffraction, then there we should always have mass of the atoms which are much higher than the usual mass of the atoms that we consider in neutron diffraction. Hello viewers, today we discussed some of the very important points in crystal structures. Those are what are the different types of crystal structure, how we can distinguish different crystal structures, what are the internal characterizations of crystals, and how to study a particular solid if we want to know the crystal structure of the solid. At the end, we have discussed about X-ray diffraction and how it is different from neutron diffraction. Hope you must have enjoyed these lectures. Thank you.